In this last subsection of talking about moments, we're going to address equivalent systems, which is going to help set us up for talking about rigid body equilibrium in the next section. So here we are typically trying to simplify or reduce one system to look like a second system that is equivalent. So we're going to define equivalent systems this way. So two systems, I'll say system 1, which will be our more complicated system, and system 2, which is typically our more simple system, are going to be equivalent if the sum of forces in system 1 along the x direction is the same as the sum of forces along the x direction in system 2, and the sum of forces in the y direction in system 1 is equal to the sum of forces along the y direction in system 2, then, at least as far as the first point goes, we have a chance that the systems are equivalent. And if we're operating in 3 dimensions, we would also need to consider the z-axis. So note here, for the purpose of talking about equivalent systems, we are not yet talking about static equilibrium necessarily. The sum of forces need not be 0 in the first system or the second system, but they do need to be equal to each other. So that's the first condition to have equivalent systems, is summing forces along the same axis in the two systems and that they are equal. And the second condition, if we sum moments around the same point in both systems, they must be equal. So in this equation here, the sum of moments in system 1 around some point A is equal to the sum of moments in system 2 about the same point A. Now it doesn't matter where A is, it just matters that it is the same point in both systems. If we sum moments around different points in the two systems, very likely they're going to have a different total moment about them, and that's okay. But with the same point, they must have the same value in order for our two systems to be equivalent. And again, as a reminder, for the systems to be equivalent, it's not necessary that their sum of forces is 0, it's that they are the same as each other in the two systems. And the same is true for the moments, must be the same as each other in the two systems. Now there's typically, at least in 2 dimensions, 2 types of simplifications that we like to make from going from system 1 to system 2. So typically, we want our more complicated system 1, which might have multiple forces and multiple couples acting on our object, to be simplified in system 2 to have just one force and one couple, and all of it's operating or located at a specific point. So we might go from multiple forces to a single force, multiple couples to a single couple, all located at a single point. A second possibility is that we want to reduce all of our forces and couples into just one force in the second system, and we need to find where to put that one force along some axis, so that again, when we sum the forces in system 1 and 2, everything's equal, and when we sum the moments around a point, everything is going to be equal. And what we're going to find again is that externally, I keep stressing that because internally is a different story, but externally, the systems are going to be identical. Again, this is checked by summing the forces, summing the moments, and seeing that they are equivalent. So why would something like this be useful to us? Why is the ability to simplify our system to a force and a couple, or one force, going to be useful? Well, we might be designing some system that's we want to act a certain way, but we want to achieve it in the simplest possible form, possibly using just one force and a couple at a specified point, for example. And this can be accomplished if we want to use as few materials as possible. We could make an equivalent system that acts the way we want to with just one actuator that's providing a force and one motor or one servo, which would be applying a couple. Instead of having to use multiple actuators, multiple servo motors, we can just put one of each at a specific point, and the system externally will act the way we want. Or even more simply, we could just put a single actuator at a specified point, and we can recreate what the more complicated system did externally. Now this would be useful more in a dynamic system, which we're going to look at in the follow-on course to this. However, the idea of these equivalent systems is still going to be important. And this idea is important going forward into the next section, where we start talking about rigid body equilibrium in 2D and 3D, because in that case, the equivalent system we want to make actually has no forces and no couples. Which is to say, when we sum forces in system 2, always the forces are going to sum to 0. When we take the sum of moments around any point in the second system, it's going to sum to 0. And we're going to then go back and look at our first more complicated system in order to figure out what's going on.